Hello. So in this video, I want to introduce logical statements and connectives to make more complex logical statements. Let's jump in. Okay. All right. So let's start with a definition for logical statements or mathematical statements. So when we say statements, I mean sentences that are either true or false, but not both or neither. So you might think, well, of course, the sentence is either true or false, but you could get like a tricky sentences like, here's a famous one, a statement, this statement is false. This is a version of what's called liar's paradox. If you try to consider the statement either true or false, you can get yourself in a loop where neither could be true. If the statement was true, then it should have been false. But if the statement was false, then it had to have been true, and then you kind of get into a loop, right? Some statements cannot be classified as either true or false. But if you want to talk about logical statements, it has to be one or the other, but not both, and not neither. Okay. So I'm going to start talking about connectives to build more complex statements out of smaller ones. It's going to get pretty abstract with lots of letters. So if you want a context, you could just kind of plug in these two sentences. So the PB, the sentence that neutrino has a mass, and QB, the sentence that neutrino travels at the speed of light. So these are physicsy type of sentences that could be either true or false. I'm not trying to make any statement about physics, but you can kind of think about more complex sentences you can make out of these two statements, just to kind of give your mind some context. All right, so let's talk about the first connective called negation. So if you use this negation symbol in front of a statement, so this looks like a negative sign, except there's a little hook at the end of the right end. So it looks like a little corner, upper right corner of a piece of paper or something. You read this as not P, and this statement is true whenever P is false. So it kind of flips the true value of the statement P. So in this example with the neutrino, not P would read something like neutrino does not have mass, right? Or it's not the case that neutrino has mass. So that's a new sentence you can create from previously existing statement. Or you could say neutrino does not travel at the speed of light if you write not Q. Okay, so that's simple enough. Not flips the truth value. Conjunction is a fancy way to say the word and, right? So the way to write that in symbols is you put a wedge between two different statements. So wedge looks like a little triangular symbol there, like maybe an exponent symbol on your calculator. This statement is true if both P and Q, the both parts of what makes up this conjunction, is true. So if you say a statement like neutrino has mass and neutrino travels at the speed of light, then P and Q is true if both P and Q were true, and it becomes false if at least one of them, those two statements, is false. So that's conjunction. Disjunction is a fancy way to say or inclusive or. So you write it with the symbol V, so it looks like a letter V. You write P or Q, and this thing would be true if at least one of P or Q or both are true. So that's disjunction. Now, the word or in English is a little bit ambiguous. Sometimes, if you put it in some context, it sometimes means inclusive or, where both are allowed to be true. But sometimes in other contexts, it's an exclusive or, where you want one of them to be true and the other one to be false, but you cannot have them both be true. For an example, exclusive or might be something like when you go to a restaurant and you order a lunch special, and maybe the menu says the lunch special comes with soup or salad. What they mean is you could have soup or you could have salad, but you cannot have both soup and salad without paying something extra. That's what they mean when they use the word or there. If they're happy with giving you both, they would just say the lunch special will come with soup and salad. So that's an exclusive or. An example of an inclusive or might be something like maybe a job ad that says something like, hey, applicant must have 2 years of experience or must speak Spanish fluently. When they use the word or there, they're happy to have both experience and fluency in Spanish when you apply, right? There, you could have one or the other or both. If you're okay with both, then you're using what's called the inclusive or. That's a disjunction. In this book, they don't explicitly give a notation for exclusive or, but sometimes people might use this symbol to mean one or the other, but not both. Okay, moving on. The next connective is called biconditional. So in symbols, you write double-headed arrow between the two statements. And when you read it, you probably say P if and only if Q. This thing is true if both sides of the statements have the same truth value. So both P and Q are true, or both P and Q are false at the same time. They can't have opposite truth values. So that's biconditional. Sometimes people say if and only if and shorten it IFF. So I think that's a good handy shortcut notation when you're writing it in your notes. But you better be a little bit careful when you use the shorthand, because when you pronounce it, people just say if. So that sounds like you're just saying if with one F, which has a completely different meaning in logic. So when you're writing it, it's fine. But when you're saying it out loud, probably you should say if and only if you want to be clear about what you mean. That's biconditional. And I think the trickiest connective here is what's called conditional, sometimes called implication. So if you have two statements P and Q, and you write P arrow headed towards Q, this means P implies Q. Or another way to say the exact same thing would be if P, then Q. Okay. This thing is true uh, if Q is true whenever P is true. I think another way to think about it is like the only thing this could go wrong is when a true statement is pointing towards a false statement. So you cannot have P be true and Q be false. Any other combination is fine. You could have a true statement pointing towards true statement, that's okay. If P is false, then Q could be anything. Q could be true or false, it doesn't matter. So the only thing that breaks down a conditional is if true is pointing towards false. Basically, what you don't want in logic is deduce something that is false when you start with something that's true. So you can kind of think about it that way. What makes conditional slightly tricky to handle is that unlike any other connectives that we've discussed so far, this thing is not symmetric. So P implies Q is not the same thing as Q implies P. That would be two different things. With conjunction, disjunction, and biconditional, all of those, if you flip P and Q, it actually means the exact same equivalent statement. But conditional, which part of the sentence comes before and after the arrow does matter. Okay. Yeah, so I think I've already mentioned about inclusive or versus exclusive or. So I'm not going to go any further than that. But if the word or is used in mathematics, by default, assume the inclusive or, unless it's specifically stated one or the other. Another thing that people might get tripped up on with the conditional is that usually in English, when you say if P then Q, if you're phrasing a sentence that way, there's a little bit of an implication that the one thing causes another thing to happen. So in logic, you do not assume any causal relationship at all. The only thing that matters is the truth value of P and Q. They don't have to be related. So for example, if I say something like, if unicorns exist, then China is on the moon. This sentence is absolutely absurd, but considered in logic, it's actually a true statement. The reason is that the if part is false. Unicorns don't exist. So it doesn't matter what is said after the then part. As long as true statement is not pointing towards a false statement, you're allowed to say anything you want, and conditional would be a true statement. So if unicorns exist, then China is on the moon. It's a true conditional statement. Here's a summary of the relationships between the true and false. So on the left-hand side in the truth table, there's all combinations of what you could have for P and Q. P could be true, Q could be false. Every combination is summed up in these 4 rows. And on the right-hand side, that tells you what the connectives are doing. Okay, so the connective not P flips the truth value of P. So if P is TTFF, then not P is FFTT. He flips the T into F, and he flips the F into T's. The connective P and Q, or the P wedge Q, this thing is true only when both P and Q are true. So this is the only time this is true. Every other combination of true and false gives you a false conjunction. With disjunction, this is a little bit more forgiving. It's true as long as there's at least one true statement in P or Q. So as long as one of P or Q has a true in it, then it becomes true. The only way a disjunction is false is if both of them happen to be false. The biconditional is true when the truth values of the two things agree. If it's one or the other, you get a false statement. And here's the implication. So the only way it could go wrong is if the true is pointing towards a false statement. Every other combination is considered true here. Okay. Couple of other words that I want to mention. If you have an implication, the sentence that comes before the arrow, the if part of the statement, is called the hypothesis. And the arrow, the head of the arrow is pointing towards the conclusion of that implication, or the conditional. And the opposite statement, so if you're talking about a conditional, and the arrow that points the other way, where Q is pointing towards P, this is a different logical statement than before. It's called the converse of the P implies Q. So if that's the converse statement compared to this P implies Q statement. Okay. So let's practice with evaluating truth values. So let's say P is whatever statement that's true, and Q is a false statement. And below I have 6 different expressions that combines one or more connectives that we used earlier. And I want you to evaluate what this expression is saying. Is it a true statement overall, or is it a false statement? So I invite you to pause this video and work out what you think what these truth values are. So go ahead. Okay, let's cover the solution. So the first sentence here, we look at the parentheses first. So not Q is going to be a true statement because Q is false. So true statement and a true statement will be true statement overall. P implies Q. So this is a situation where true statement is pointing towards a false statement. So the implication part is false, but there's a not symbol in front. So you flip the truth value. This becomes true overall. The next sentence, you have not P. So P is a true statement, so not P is a false statement. If the hypothesis part of the implication is false, then it doesn't matter what comes after the arrow. This becomes a true statement. The next expression, you're using the not twice. So you flip the truth value twice and you get back the original truth value, true in this case. Okay. The next statement is a disjunction, right? So P or Q, one of those is true, P is true, so that makes the whole disjunction true. But there's a not in front, so that will flip the truth value and you get false in the end. And here, P is true, and true statement is pointing towards the disjunction P or Q. So there's at least one true here. So the conclusion part is also true. So true can point to true, that's okay. This is a true statement. Okay, I hope that made sense. Let's do a few more words. I want to cover the concept of logical equivalency. Okay, so remember previously we discussed P and not P. So if you flip the truth value twice, you get back to what you started with. So P is equivalent to not P. So I'm gonna write logical equivalence with something that looks like an equals symbol, except there's like 3 parallel lines except instead of the usual 2. The reason why I'm using a distinct notation here is that if I say equal, it looks like I'm saying the truth value of the left and the right hand side is equal. But what I want to say is something that's stronger. Logical equivalency means the left and right hand side is equal for any possible combination of true and false values you can assign to all of the statements. So here, I can assign any possible truth value for P and Q, and then no matter what I plug in, the left and the right hand side will have the same truth value. So if I say it's not the case that both P and Q are true, that's equivalent to saying either it's not P is not true, or Q is not true. If you say it's not the case that P or Q is true, that's the same as saying P is not true and not Q is not true. Right? So both of these are sometimes called De Morgan's laws. If you're a computer science student, maybe you have seen it in other classes. But that's one way to think about it is that if you have the not, logical not, and you want to distribute that through parentheses, you could do that, but you have to flip conjunction and disjunction. So here's an and symbol that turns into or symbol. If you start with the or symbol, you flip that into and symbol after you distribute the not signs. So that's kind of a mental shortcut you could use in symbols to help you evaluate the logical equivalency. Okay. A couple other useful logical equivalency is if the opposite of implication. So if it's not the case that P implies Q, then you get P is true and Q is false. So that's another way to state the exact same statement. This is a really useful one. I'm gonna box it. P implies Q. Sometimes it's easier to look at the opposite direction, but remember, P implies Q is different from Q implies P. An equivalent statement from backwards point of view is not Q implies not P. This is called contrapositive. So sometimes if you have an implication, it might be easier to prove the contrapositive statement instead. So you change what the problem looks like, and maybe it's a little bit easier to write the proof in that case. Another equivalency, logical equivalency, is that the double implication P, if and only if Q, you could break that up into two statements, two implications. P implies Q, and then Q implies P. So as you take one implication and you flip it and you prove the opposite direction as well. If you prove these two things, that's equivalent to showing that they're P if and only if Q. So you could use that to break down the proof into two steps. And sometimes that's easier. Another couple phrases that I want to talk about. Any logical statements that's always true, no matter what you plug in for P or Q or in any logical statement that's involved, that's called tautology. So if you write down something like P and Q implies P, well, I mean, if P and Q is true, then that in particular means P had to have been true to begin with. So this is always going to be a true statement. There's a couple other tautologies here. So here's a famous one, William Shakespeare, P or not to P or not to P. They're both, one or the other has to be true. So it's a tautology. So these type of statements sounds correct when somebody says it, but really there's no logical substance to it because you're saying something that has to be true no matter what. If you listen to some politicians talk, you might find that they say things that are tautological all the time. Because like it makes them sound correct. Oh yeah, what they're saying is definitely correct. But they might be saying something that's not very, that's obvious, that has to be true no matter what. So that's tautology. Kind of opposite end of that is something that's always false. So, but in particular, anything in the form of some statement and the opposite of that statement. This is called contradiction. So this is going to play a very special role when it comes to proofs. So this is something that you'll get very intimately familiar with. But I think I want to end the video here. So I will see you next week.